The core reason for the success of physics is that this gloriously rich and complicated world is, at its heart, far simpler than it first appears. From a tiny handful of rules, we can explain everything we can see, and it turns out quite a number of things that we can't yet see. Now, physics as a discipline has two main roles. The first is the study of emergent phenomena, how very simple things and their simple dynamics can evolve into very complicated behavior and patterns. And this is important for two reasons. The first is that that's the world we live in. Okay, we live in a complicated world that is made up of something that is microscopically very simple. And secondly, there are often strong similarities and powerful things that we can predict about very otherwise disparate systems because of their similar mathematical underpinnings. And we touched on this kind of thing, this sort of role of physics, somewhat gently in the classical mechanics section of the course, when we actually looked at how things really behave. In particular, chaos is a good example of that. The other main role of physics is to go deeper, is to explain more and more with less and less, to really find out what the fundamental rules of our universe are. And this course is focused on those fundamentals. Although it was not only three separate topics, classical, quantum, and special relativity, we saw a wealth of deep connections between all of those across the entire base of physics. So possibly the key message out of this course is just how important the action is to all aspects of physics. For particles, just simple discrete particles in a kind of classical world, the action is just the integral of the Lagrangian, and those particles evolve according to the principle of least action, which means we have an Euler-Lagrange equation describing their coordinates. For fields, we discovered there was action as well, except this time it was more naturally written in terms of Lagrangian density. And in that case, the corresponding Euler-Lagrange equations were in fact partial differential equations. Classically, the action is minimized. In quantum mechanics, we discovered that the action was also important. In quantum mechanics, the action defined the propagator via the path integral. In other words, it defined exactly how all wave functions evolve. We learned another critical thing, which is that physical relationships have to look the same in all inertial reference frames. The easiest way to enforce that is to embody all physical relationships in terms of tensors. And because we live in a Minkowski spacetime locally rather than Euclidean spacetime, all of those tensors should in fact be Lorentz tensors. They should be 4 vectors and 4 tensors and scalars. We looked at electromagnetism, where we start to relate the 4 momentum and the 4 velocity to the electromagnetic tensor. Electromagnetic tensor is defined in terms of the 4 potentials. The momentum for a massive particle or a massless particle always looks like this. And for a massive particle in the limit, this looks like the normal non-relativistic momentum multiplied by gamma. The electromagnetic field obeys Maxwell's equation, where this 4 current is just the density and the relativistic 3 current. Maxwell's equation isn't quite unique, it's unchanged for all choices of gauge. And indeed, it can be extracted from the Lagrangian density. Again, where this is explicitly a scalar and independent of whichever inertial reference frame you're in, because it's a contraction over tensors. In quantum mechanics, we're also often dealing with fields, and so we need to come up with field equations. The relativistic version of the free particle for just a scalar field is the Klein-Gordon equation. And while being relativistically invariant, which we can see again because it's constructed out of scalars and contracted tensors, while being relativistically invariant, it isn't in fact physical for a single particle because it leads to interpretations that don't work, for example, negative densities. It can be derived from the following Lagrangian density. As an aside, although technically you might have to split a complex valued field into a real and imaginary field, in other words, have 2 components in order to calculate your principle of least action, in fact, it's a lot more convenient and useful to treat the complex valued field and its complex conjugate as linearly independent, and that works fine for all the fields that we're dealing with. So the problems with the Klein-Gordon equation were addressed by Dirac, who discovered that in order to describe a relativistically invariant electron, he actually needed 4 components. And he had to introduce 4 matrices, therefore, to construct a relativistically invariant wave equation. So this is the Dirac equation. These are the Dirac matrices. There are 4 of them because we've got one for each space-time component, and there are also 4 by 4 matrices. And so this is a 4 vector, and that involves the spin up and spin down electron and the spin up and spin down positron. You have to be a little careful at interpreting individual components in this vector as those objects, the spin up, spin down, electron and positron respectively, because as we change frames, actually the components rearrange. And so there's a very frame-dependent interpretation of those coordinates. So the Dirac equation really hammered home to us that demanding that physical relationships are frame invariant doesn't just change our equations of motion, it also enforces particular structures upon us. And indeed, we want to do one more thing in this course. We want to describe one last fundamental principle that's informing all current attempts to unify modern physics, gauge symmetry.